It is visible.
And my pointer.
Yes, yes, visible.
Yes, yes.
Oh, hello. I am Surojit and I am presenting a action principle in physics. So my contents are I will first motivate you through that how why action is so important in physics. In classical mechanics we will discuss in classical context we will discuss the role of action, and in quantum mechanics in the particularly in the path integral formulation how action plays important role we will discuss. And in the later half of the discussion we will discuss about uh, expressions of action in a relativistic point of view, like in case of free particle and particle in a weak gravity and particle in electromagnetic field. So let's get started. So what is the action? Mathematically, one mathematician would say that action is a functional. A functional means you input a function, it will generate some sort of value. Like in classical mechanics, we assume that a is a function of path and endpoints, and most of the cases endpoints are fixed. So we will ignore that part also in whole of the lecture. But it to be noted that it is a kind of functional, like area under a curve. If you give a function, it will generate some sort of value. So in the classical regime we know that it action is defined as l integration l dt, where l most often l has the form t minus v for conservative systems. And what principle of least action says that a dynamical system evolves from one space-time point to another in a way that in which the action is minimum, in a path in which the action is minimum. Mathematically it is given by the equation 1. What is meant by the variation of path is that we assume some sort of initial function and add some sort of extra function to it, and where eta t vanishes at the endpoints, and we do some sort of variation calculation and we get this equation, and the endpoint terms vanishes as at the endpoints of 0, and we arrive at the famous Euler-Lagrange equations in equation 3. So I will move forward to the quantum mechanics point of view of action, and with introduction to the famous double slit electron double slit experiment. What is electron double slit experiment? We all know that there will be two slits, and there will be detector on the screen, and some sort of source which is emitting electron or some sort steel balls, in classical point of view. uh, if the experiment will done with bullets or steel balls, it will generate some sort of pattern like that. But if we do the experiment with electrons, it will generate some sort of interference patterns. Interference pattern emerges out of the experiment, which immediately implies that electron has some sort of probability for going through slit 1, and some sort of probability for going through slit 2 to the detector. But is the probabilities help describe the interference pattern? The answer is no, because probabilities, as we know, probabilities are semi-definite positive quantities. It would not explain the minimas in the interference pattern. So one deals with the probability amplitudes for each path through the slits. For slit 1, there will be some sort of probability amplitude, and in second slit there will be some sort of probability amplitude. I caution you that probability amplitude is a complex number with some sort of phase, so we can add them up with destructively, and they can cancel out and generate minima. So our intensity becomes the net amplitude through slit 1 and 2 and mod square of that, where a1 is the amplitude electron going from point 1 to point 2. So we will move forward, and the things we have learned from two-slit experiment, it will be more beneficial for us in formulating our path integral formulation of quantum mechanics. And the things we have learned is that a particle can take many possible paths between two space-time points. You can see this image. We have given many slits in between 2 points, and there is many possible path that a particle can propagate quantum mechanically, and there is unique probability amplitude associated with each path. So what we do is that the net amplitude for particle to propagate point A to point B is given by amplitudes for all paths, all possible paths, given by equation 5, and our dynamical equation is given by equation 6, which is psi x2i, and given by psi x2i integration the g function, which is net amplitude for propagating through two space-time points, and psi x1 is the probability amplitude for particle being at x1 I space-time point, and dq xi. I caution you because the x2 I is space-time point. It has time component and space component tx, and the integration over is only the initial spatial coordinates. So it will be kept in mind, and then we postulate our main postulate in the path integral formulation, that amplitude will depend upon exponential sum I a by h cross, where a will depend on path, because it's relevant that each path will have unique probability amplitude to particle to propagate. So it will only depend on path. So we know that paths are very important in this case. And now we never claim that A must be action, but it will turn out that A should be like action. In the next slide we will see that. We'll the 5, 6, 7 are most fundamental principles of path integral formulation, and we will build upon this in the next slide. How classical mechanics naturally emerges of path integral formulations of quantum mechanics. We know we have written down the expression for amplitude from the previous slide, equation 7 to equation 5, and we get these equations. So in the equation, in this equation, when h cross turns out to be 0, and this weight behind the exponential is take unity as all paths are equally probable, and we take this to be 1. All the contribution when h cross goes to 0, all the contribution coming from distinct paths will vanishes, because the this function has modulus 1, so it will either be +1 or -1, and there is many paths possible. So if there is distinct paths, they will +1 and -1 will cancel each other, so most of the path will vanish, and the only path that will stick out, or better to say will contribute to it, is that the path condition, the path satisfies this condition, del a by del path is equal to 0. And if we now define this a quantity, which depends upon only on the path and endpoints also, like L dt, we will get back Euler-Lagrange equations. So we can see that path integral formulation is more natural in quantum mechanics, and we will, in the context of field theory, we will do similar kind of thing in the field theory, quantum field theory also, in the Lagrangian formulation of field theory. And next we will discuss the action and the expression for action in the for relativistic free particle. So as I pointed out that action is a functional, so the best choice would be the path length, because a quantum particle can propagate through different paths, and what could be the best choice for it to be a action, because if we take action as a path length in space time, it will be automatically for different paths its value will be different. So it is general to take the path length in space time, but uh, in classical physics there is no notion of space time path length in classical physics, because in classical physics we always treat time and space separately, they are not coupled. So but in relativity we can, there is a space time interval in general relativity which is also Lorentz invariant, that will provide us Lorentz invariant theory altogether. So we defined our space time interval such where d tau is a proper time interval which we all know, and we take our action to be minus k dot integration dot ds integration ds, and the calculation, the minus sign will be relevant soon in the next step, and we take out general expression as we did in the special relativity, and in the by using dimensional regions, because action should have dimension of Planck constant, so it should be dimension have it should have dimension like angular momentum, and this part apart from dt it would have dimension of energy. So this part is dimensionless as we can see clearly, and so k should be mc. So if we expand in the non-relativistic limit v much less than c, and the Lagrangian will come out as half mv square minus mc square, and further we can neglect the mc square part by arguing that Lagrangian can be transformed into some L plus some function del lambda by del t, which is lambda is a function of x and t. So we can explain the Lagrangian, we can explain the Lagrangian from relativistic point of view also by arguing the space time, the length in the space time would be natural choice. And now we will discuss action for a particle in a weak gravitational field. We claim that
You
in the
have three
presence of,
minutes left. Okay.
okay, okay, uh, we claim that in the presence of weak gravity, the curvature of space time depends upon spatial coordinates, because uh, now in this position we can claim that our metric depends upon this kind of, by equation 12, depends upon where phi x is a gravitational potential, and this equation has severe implications, that the clock in a deeper potential will slow down, and we will prove these claims by using principle of equivalence, the most beautiful principle in physics, which states that inertial and gravitational charge are equal. What is principle of equivalence? It says that acceleration and gravity are the same, because inertial mass and gravitational mass are same, or rather gravitational charge are same. So acceleration can mimic gravity. In this picture we can see that a man standing nearby earth in a box will feel the some downward pull, but the man in the rocket also feels some sort of downward pull, but in this case the man in free space, but its rockets are accelerating uh, with acceleration due to gravity in the upward direction, and it also the person also feels it is pulling downward. So we can set equivalence between those 2 points, those two pictures. So we claim that freely falling motion can counterbalance gravity. Now we look at this picture. A person in gravitation in earth feels the gravitational field, and the person is freely falling. So we get that a freely falling observer will not get any gravitational field. So it will be, he will be in an inertial observer, and we suppose that he has a clock, and we have some clock set in the box also, and the man will see that clocks in his reference frame, the man will see that the clocks will go upward direction. So so our this relation will hold in that case, because in special relativity we already dealt with accelerated frames now. So we'll this equation will satisfy, where dt phi equal to 0 represent the time in the inertial observer and in the frame of the man freely falling, and dt phi will be the reading of the clocks attached to our box. And by conservation of energy, we get that half mv square equal plus potential energy would be 0. As the person freely falls from the infinity, the potential energy will be 0, as we know from our school days, and the kinetic energy will be 0 as the person freely falling. The initial kinetic energy would be 0. So we get equation 13, and we have proved our claim. So in this case, by similar arguments, we can get the action for particle in a gravitational field like 1 plus 2 phi by c square minus v square by c square to the power half dt from this metric
Your
tensor
time is
argument.
over.
That give me 2 minutes. It's already completed. I will take 1 minute also. So on the non-relativistic limit, the Lagrangian becomes like half mv square minus m phi plus some sort of boundary terms which we neglect by similar arguments as we claimed previously. And the main comment I would make that Lagrangian need not to be the form kinetic energy and minus potential energy, as we have seen that in that case, or in the free particle case, it is for the more exact system, it is not like kinetic energy minus potential energy. In the non-relativistic limit, sometimes it gives kinetic energy minus potential energy, it's true, but in more exact cases, it's not coming kinetic energy minus potential energy, it's rather else. And action and electrodynamics, similar arguments we can also do and rederive our electrodynamics wholly by contracting some 4 vector with dxj, and we will get by varying the similar sort of arguments, by varying the action, we can get Lorentz force law in tensorial form, where Fij is a electromagnetic field tensor and Ai is phi and A. The resources are Feynman lecture notes volume 2 and quantum mechanics by Sakurai. Thank you. It's
Okay,
over.
Surajit. Yeah. Okay. Tell me, what is the physical significance of action? What do you mean by action? I mean, apart from the mathematical definition you have already told.
Action is a functional. If you provide some sort of action, some sort of path